we're going to be given a scenario where we will have unknown samples of organic substances. Now, all of these organic substances that we're going to be given are going to be liquids at room temperature, and they're going to be colorless. So we can't identify whether they are alkenes, alcohols, haloalkanes, alkanes, amines, or carboxylic acids. However, there is a series of tests that we can do to identify what type of functional group they do have. So the tests we're going to look at in the next couple of slides are adding bromine water, adding permanganate solution, adding acidified dichromate, acidified permanganate, water. You can bring haloalkanes close to a charged particle. You can use red litmus for test for amines. You can use blue litmus to test for carboxylic acids. And you can add carbonates to test for carboxylic acids. So let's just go on and have a look at some of these examples. Okay, so the first example that we have here is what's called a permanganate test for an alkene. So if we take a sample of an alkene, and it could be something like cyclohexene or hexene, and we add some purple permanganate solution. Now remember, it doesn't have to be acidified. Sometimes they might have a /H+ to show it's acidified. It won't make a difference. When we add purple permanganate to the alkene and shake it, it goes brown. So it goes from purple to brown. Now if we see, this is the reaction that happens. We have a double bond. It produces a diol. It has undergone an oxidation reaction. And the positive test, remember, for an alkene here is we added permanganate and it changed from purple to brown. So we can also do a test for alkenes. We can do what's called the bromine water test, and we take a sample of it again. We add some bromine water to it, and then we give it a shake. Now, and then if it changes, it goes colorless, and within 10 seconds, then we know that we have an alkene. Now, what's happened here is this is an addition reaction. What's happening here is the two bromines from the bromine molecule, the double bond breaks, and then they add to the place where the double bond, to the carbons that were part of the double bond. So we get two bromines added. Now, this has undergone an addition reaction to produce a haloalkane. And the solution for this bromine water test is a positive identification for an alkene as the solution changes from orange to colorless. We can also just do if we do a bromine test with an alkane or any other organic molecule that doesn't have a double bond or a triple bond, then the following will happen. If we add the bromine water to, let's say, a sample of alkane, it's going to stay orange. But if we put it in the presence of ultraviolet light, what the ultraviolet light does is it will actually react with the alkane chain, and it will radicalize one of the hydrogens and remove it, and then that will react with the bromine. So it will take 30 minutes. So it's actually not a definitive test. Any organic molecule is going to do this reaction with bromine water. It takes a long time, over 30 minutes, in the presence of ultraviolet light. Now, this is not a positive test for, it isn't a positive test for alkanes because all organic molecules have alkane molecules. However, we do know that a substitution reaction has happened. Okay, so often what will happen is you will carry out the bromine water test on both an alkane and an unknown alkene, and the one that reacts and changes color from orange to colorless very quickly we know is the alkene, and the other one must be the other molecule, the alkane. So if we want to do a definitive test for a primary alcohol, or if an alcohol functional group is present, what we can do is we can either add acidified dichromate or acidified permanganate. With the acidified dichromate, we'll take a sample of the alcohol, and then what we'll do is we'll add to it a solution of acidified dichromate. Now, sometimes you'll get the solution is already made up, the dichromate acidified. Other times you might add some unacidified potassium dichromate and then some acid as well. But if you don't make it acidified, it's not going to work. So we add the sample to here. It's orange for a start. We place it in a water bath for about 5 minutes. Sometimes it reacts quickly, sometimes it needs a bit of heat to make the reaction happen, but it will go a green-blue color. It will start becoming more green and then eventually become green, and if you leave it for long enough, it'll go a bluer color. Now, this is because what's happening here is the alcohol group is turning into a carboxylic acid functional group, and at the same time the dichromate molecule is turning into the chromium ion that is a blue-green color. Now, this is an oxidation reaction, and this is a definitive test for alcohol groups. It can be used also for aldehyde functional groups, but at level 2 NCA chemistry we don't need to know about those. So the solution changes from orange to blue-green. If we could use acidified permanganate, which is another oxidizing agent, it is purple. Its formula is MnO4 minus, and there's a /H+ because it has been acidified. It has acid with it. Now, if the sample, purple acidified permanganate is added to the sample, we can put it in a water bath and heat it for 5 minutes. It will go colorless. This usually goes doesn't need to be heated and will react it itself anyway, but it does go colorless, and that's because the permanganate ion that the manganese ion the permanganate turns into is colorless. So again, what we've done is we've taken a primary alcohol and we've turned it into carboxylic acid. This is also an oxidation reaction, okay, and it is the color change we need to remember here. It's going from purple to colorless. Okay, so let's look at how we might test for amines and carboxylic acids. So essentially we're going to test them in the same way that we would for acids and bases. So amine, we're going to use red litmus paper. The first thing we're going to do, however, is because when we use litmus paper, we have to make sure that the sample has mixed with water to produce the hydroxide ions. So we take the sample and we add it to some water. So we now have an aqueous solution. And then we take that solution and we dip the litmus paper in it, the red litmus paper. And if the red litmus paper goes blue, there we have it, we have an amine. Now the reason that worked is because when we added the water to the amine, what happened is the water donated a proton to become a hydroxide ion, and the hydroxide ion will react with the litmus paper to make it turn blue. Now, amines are weak bases, partially dissociate, produce hydroxide ions. The observation we're looking here is damp litmus paper, damp red litmus paper turns blue. If we want to test for a carboxylic acid, we're going to use a blue litmus test. Okay, and we do exactly the same. We take some water, we put our sample in the water, we mix it, we take our blue litmus paper or blue litmus solution, and it will go red if it is an acid. Now again, what's happened here is the carboxylic acid has reacted with water, it's donated its proton and produced the hydronium ion. The hydronium ion causes the blue litmus paper to go pink or red, and remember we need the water for this reaction to happen, so we make sure that there's two ways you can do this. You can mix the sample with the water, or you can make the litmus paper, put it in water, make it damp for a start. So the positive test here is our litmus paper, damp litmus paper, will go from blue to pink. Okay, the other way, so the definitive test, so if we think that we have a carboxylic acid because it went pink, we're going to definitively test this or make sure by taking the sample and adding to that sample some sodium carbonate. Now, the sodium carbonate is going to react with the acid, with the carbonate ions from the sodium carbonate is going to react with the carboxylic acid, and it's going to make it's going to make carbon dioxide and water. Okay, so that's what it's going to produce, and we will see the carbon dioxide as bubbles. That's our observations. So carbon dioxide gas, positive observation for this is the solution fizzes or gets bubbles. Okay, so the other test that we might use here is called a physical test that we're going to carry. There are a couple of actual physical tests we might carry out to identify, distinguish between different organic products. The first one is solubility test. So what we do here is we see whether the organic substance will mix with water or not, whether it's miscible in water. That means that when we mix the sample and the water together, it just forms one layer instead of two layers. So what we take is we take a sample of water. So we take some water and we add the sample to it, and then once we have these two in the same test tube, we give it a shake. And if the experiment here, or what's in the test tube, only forms one layer, then it's because this molecule is soluble, and it's because it forms hydrogen bonds with water. So if there's a single layer after the sample has been added, it means that, okay, the sample that we've added must be an alcohol, an amine, or a carboxylic acid that has 4 carbons or less. So it must have an alcohol group, an amine group, or carboxylic acid groups, and it must have less than 4 or less carbons in its chain. Now, what actually happens here is, here's an example of an amine. So the amine will actually, these lone pairs that are found at the top of the nitrogen here will form an attraction with the hydrogen particles. Okay, so another physical property apart from solubility we can use to distinguish organic molecules is their boiling points or the melting points. Often we're going to use boiling points because most of the samples of organic substances we have are going to be liquids. So what does that mean? So boiling points, if we're going to separate two things from their boiling points, we need to know the following. The melting and boiling points of organic molecules in a homogeneous series. This is a series that have the same functional group but increased by 1 carbon atom each time, like methane, ethane, propane, butane, pentane, hexane. That's homogeneous series, or we could do the same for alkenes or alcohols. As they increase the number of carbons, their melting point and their boiling point gets higher. For example, here's a table of the boiling points of the straight-chained alcohols: methanol, ethanol, propanol, butanol, pentanol, and hexanol. And notice how, as the number of carbon atoms of the alcohols increase, so does the boiling point, from 65 degrees Celsius up to 157 degrees Celsius. Now, that occurs because as we increase the number of carbons, we increase the number of hydrogens, and actually the molar mass of the molecule is increasing. If we increase the molar mass of the molecule, they have stronger attractions to each other, and that means more energy is needed to break these attractions, and therefore their melting points and boiling points are higher. So what is the type of experiment we can do to identify these two different types? Well, what we can do is we take a water bath, right, or a container, a beaker full of water, and we put our two samples, A and B. Now let's say one sample we know is methanol and the other we know is ethanol, but we don't know which is which. So two different samples of alcohols. Well, if I heat this, and if I start to heat this water, so this is colder water, tap water, as I heat the water up, the sample that boils first is the sample that boils at a lower temperature, and that is the sample that has the weaker attractions and the smaller molar mass, and it will be the smaller molecule. So the smaller molecule will start to bubble or start to boil first. So this test that we used here is the sample that boils first must be the sample with the smallest number of carbon atoms. Now, we can only use this test if both of these molecules that we have to distinguish between are in the same functional group. They're all alkanes, or they're all alkenes, or they're all alcohols. And that is how we could use how we could use this water bath test to determine the boiling points and hence distinguish between two different organic molecules in the same homogeneous series. Often we're going to be given a scenario where we will have unknown samples of organic substances. Now all of these organic substances that we're going to be given are going to be liquids at room temperature, and they're going to be colorless. So we can't identify whether they are alkenes, alcohols, haloalkanes, alkanes, amines, or carboxylic acids. However, there is a series of tests that we can do to identify what type of functional group they do have. So the tests we're going to look at in the next couple of slides are adding bromine water, adding permanganate solution, adding acidified dichromate, acidified permanganate, water. You can bring haloalkanes close to a charged particle. You can use red litmus for test for amines. You can use blue litmus to test for carboxylic acids, and you can add carbonates to test for carboxylic acids. So let's just go on and have a look at some of these examples. Hey, thanks for watching this video. Hopefully this has made you more confident with your chemistry. Don't forget to like, subscribe, or leave a comment about anything that you want to with this video or any questions you have. I'll see you later.